Hello and welcome back. As you probably know, my name is Michael Hansen. I have a master's degree in physics from the University of Copenhagen and is currently employed as a part-time astronomy teacher at Roskilde High School, or as it is actually called, Roskilde Gymnasium, which is a high school here in Denmark. Not far away, so that's actually pretty nice. In this video and the upcoming, I think, 2 or 3 videos, I'm going to work a little with some videos made by a guy. I think he calls himself Phuket Word or Phuket Word or something like that. I'm not sure how he actually wants that name represented, because Phuket is, as far as I know, a city or an island, and word is a word. So I'm not sure what he's actually trying to mean with it. In this video, he's trying to sort of show that if the sun was going below the horizon, then the shadow of some object should be higher than the object itself. Let's take a look at what he's going to say.
Hello, Flat Earth researchers, debaters and debunkers. I'm going to do a quick and very easily repeatable experiment using light and shadows with this torch representing the sun and casting shadows on the wall from this bottle and box on the table, so that we can...
Let me just stop him right there. Let's just imagine. It doesn't seem to me that this guy has any notion or any idea about how many errors of judgment and assumptions that he's putting into this experiment. First of all, the notion of reasonable differences in sizes. So the sun is so incredibly large compared with the Earth that we can basically see the sun rays, if we sort of could measure a sun ray going towards the Earth, as linear rays coming towards Earth. So they're not spreading out, they're coming with equidistance between each other, or how you'd call it, in the same angle. Whereas this torch that he's using here is spreading light out in a cone. As you can also see it on the wall, it's a round cone. So already there, and also the distance, if he were really trying to do this experiment, he would have to have an incredible huge lamp and then move many miles away to make this experiment. But nevertheless, let's continue and hear what he has to say about whatever it is he's doing. So let's see.
Compare what should happen to shadows if the sun is going down below the curve of a globe, with the table edge representing the edge of the globe, and then with the sun just getting farther and farther away, as it does on the flat Earth. Over here I have a marking on the wall which is at the same height as the bottle. So of course what should happen is, if the sun is only above or at the same height as the bottle, the shadow of the bottle will go no higher than the bottle itself. So if that bottle was a building casting a shadow at sunset on a building next to it, if we are on a flat Earth and the sun just gets farther and farther away, then we would see a shadow that never goes higher than the height of the actual object casting the shadow. However, if the sun is going down below a curve and therefore lower than the object itself, then of course the shadow goes higher than the object itself. So it's a very simple comparison that you can make with the sun.
No matter how little I really want to admit it, he really, in some sense, have a point. His experiments is flawed in so many ways that I can't even count them. But he is actually saying something correct. So let's just go on with that assumption and say, if the sun is going down on a spherical Earth, then at some point some very high or very tall object would have to cast a shadow larger than itself. I'm going to show you that here on the whiteboard. So as you can see here on the whiteboard, when the sun is out here going down, and obviously that is sort of a not real true drawing. Let me just correct it a little bit, because since the sun is setting, it would be somewhere around here, and as you can see, it would cast a shadow larger. For example, this mountain here, this area here would be in shadow. So that's correct enough. But you have to have something really big in order to notice it, because otherwise the sun and the comparison with sizes and all of that, you won't really be able to measure it to any true degree. And also, if you're, for example, in some city or whatever, some things might obscure your view, but you can actually just think about it in any true sense. In a simple thought, if you have something really big in front of you, which is just a tad above the horizon, for example a big box, and then you sit down behind it, so and you have a clear view out to the horizon, like an ocean or something like that. So when the sun sets, and the box have to be higher than the horizon, of course. If the sun not sets but it's going down, it sets. If the sun sets, then at some point the sun would go below the box. You can't see the sun more for the box, and then obviously the shadow of the box is higher than you. So even if you are higher up than the box, but you can't see the horizon, then at some point the sun would go below the box, not below the horizon, but below the box. And since you can't see the sun, obviously the shadow of the box is going above you. So that's a very simple experiment that you can do. But let me show you what would happen on a flat Earth, where the sun is just moving around us. And let's say that the sun is sort of further, it's very far out. So let's show you. Let's see what happens. Now, this drawing here is extremely exaggerated, because obviously if the sun is above the mountain, then there would never be any rays coming at this altitude here. They would be more like these. But the idea, the point with this drawing here is to show you that on a flat Earth, the shadow would never ever become higher than the object itself, unless the sun begins to go further down. Actually, not just perspective, as flat earthers love to use, but actually physically go below the mountain. Not below, but in less altitude than the mountain. So, even though I don't agree with this kind of experimentation, because there's so many errors of judgment and assumptions intertwined into this experiment, and even the basic assumptions is not in place, because he's actually comparing a light source with a definable cone with a light source that is so big that there's no cone, that the light is parallel, the light rays are parallel. But nevertheless, his point being that we are on a flat Earth because shadows don't seem to rise higher than the object itself. Let's see if I think that's his point.
just getting farther and farther away, not making the shadow go any higher than the object itself. But if the sun is going down any lower than the object, the shadow of the object will go much higher than the object itself. So you can make this observation absolutely anywhere, in a city, on the beach, in the countryside, a tree, a post, a stick in the ground, a building, a statue, whatever. If the shadow of the object never goes any higher than the object itself, then you know the sun is just getting farther and farther away. If you see the shadow go higher than the object itself, you know the sun is going down below the curvature of the earth. Simple, easy, repeatable science. Thank you very much.
Simple, easily repeatable science. Yeah, to some degree. No, I'm sorry, his point was actually not that. His point was to, as I actually want to compliment him from, is making an open question. If you see one thing, then you can conclude this. If you can see another thing, then conclude this. Alright, so let's say if an object casts a shadow that is higher than the object itself, then we can conclude that the sun goes below the horizon. So if the earth was indeed flat, then could someone please tell Mount Rainier here not to cast a shadow on the clouds? Because obviously those clouds are not further down than the mountain itself. And with that image in your mind, imprinted forever, I will say bye bye and thank you for watching. Hope to see you again.